Hey, fellow mathers! Welcome to the podcast where math is figure-outable. I'm Pam Harris, a former mimicker turned mather.
And I'm Kim Montague, a reasoner who now knows how to share her thinking with others. At Math is Figure-Outable, we are on a mission to improve math teaching.
Did you just say now's knows?
Probably. Just move on, Pam.
We know that algorithms are amazing historic achievements. But y'all, they are not good teaching tools because mimicking step-by-step procedures can actually trap students into using less sophisticated reasoning than the problems are intended to develop.
In this podcast, we help you teach mathing, building relationships with your students and grappling with mathematical relationships.
We invite you to join us to make math more figure-outable. Bam.
This is a no mocking zone.
I'm sorry. I wasn't trying to... That wasn't mocking. That was me just... I was noticing. I see you, Kim.
Oh,
I got your back. That's what I meant.
Hey, last week we talked a lot. It was a big episode.
Oh my gosh. We both looked up. It was like, whoa, that was long.
Yeah.
All right.
It's good stuff though, right? All right.
Yeah,
so last week, we're just going to dive in because we have so much to say about fractions.
Go.
So last week, we talked about making meaning of a unit fraction by a unit fraction and all the different things that come into play with that where kids are reunitizing. And it's really important that we spend that time and we spend that work rather than just tell them to multiply across because then we can build on it. So let's build on it.
Yeah, and you just said a unit fraction by a unit fraction, and I'll add two other ways to say that. So a unit fraction times a unit fraction, and a unit fraction and a unit fraction of a unit fraction. Yeah, so three different ways that we want to build all of those, and it's more than just telling kids of means times or times means of. Either way, it's really like let's get those three meanings down. So y'all, if you're just tuning into this episode and did not listen to last, you are gonna want to listen to the last one. By the end of it, we were like, kids now have some sense of a unit fraction, 1 in the numerator, times another unit fraction, 1 in the numerator. So like 1/5 times 1/7 or 1/3 times 1/4. They're not just multiplying straight across. They are really reasoning that they've got if it's 1/4 times 1/5, let's do another example. If it's a third times a seventh, then they've got 3 times 7 total number of pieces in the area model, and they can think about that, and they can think if they've just got one of them, or they can really think about 1/7, and that there's like 7 of these chunks. They can cut one of those sevenths into, what did I even say, 1/5 of a seventh? Into 5 pieces, and so they could really think about, then they'd have 35 total pieces, and they've got 1 out of those total pieces. So anyway, we kind of got that down. Kim, one of the things that we would really want to have before we dive completely into multiplication of fractions would be to have kids think about 5/7, a fraction like 5/7, not only as 5 out of 7 equal pieces, but we would also want them to think about 5/7 as 5 1/7.
Yeah.
In fact, in our challenge that we just did a few weeks ago, we did a fraction problem string, and in that fraction problem string, when I would talk about fractions like 3/4 or 2/3, I would often say 3/4, and I would say 3 1/4, or 2/3, and I would say or 2 1/3. And we had several challenge participants ask, like, why are you naming fractions that way? And so I would suggest that thinking about 5/7 as 5 1/7 really helps kids get a more multiplicative view of 5/7. If it's just 5/7, then I could just count 5 and count 7, and then that's 5 out of 7, and I could really be only in counting strategies. But if I can think about 5 1/7, 5/7 as 5 1/7, I can think about it as 1/7 plus 1/7 plus 1/7 plus 1/7, like 5 of those 1/7. That's more of an additive thinking. It's kind of like skip counting. And then I can move from that to thinking about, well, I've got 5 of those 1/7, and that's a bit more multiplicative. I can really think about 5 1/7. That's like a scaling view. I'm scaling 1/7 times 5.
Yeah, and I think it helps kids recognize that you have 5 of those 1/7. It's not that 5/7 is this random weird amount that isn't connected to any other amount.
It's not like 5 pizza pieces out of 7 pizza pieces. It's 5
of the 1/7.
Of those 1/7. Yeah.
Yeah. So and fractions becomes this time or this place where kids may start to think it's all about rules, right? Because some of the things that we say, but this scaling idea that you're talking about really is and can be connected to some work that they've done in multiplication.
Work we would hope they have done in multiplication.
Yeah. Work we've hope. So when we talk about 25 times something, we can scale that to get 75 times something. Or for smaller numbers, if we're finding 20 times something, we can find 10 times something and double it, scale up times 2, or find 2 of something and scale up times 10. So they're, if they're experiencing scaling in multiplication of whole numbers, then it's not such a reach when we're talking about scaling with fractions.
Yeah, nice. So if that went really fast right there, then check out some of our multiplication episodes, or maybe we'll just do one on scaling and multiplication one time. Anyway, so today, let's build some multiplicative reasoning with fraction multiplication and think about this idea of how we can bring scaling into it.
Okay.
All right, Kim. So the very first problem I'm going to give you is 1/4 of 1/5.
Oh, okay. So that's going to be 1/20. So
you can say more.
Do I need to talk about it? I mean, we did last episode.
Yeah, listen to last episode. Okay, so if 1/4 of 1/5 is 1/20, then what might be, or maybe I'll just say next problem. What's 3 1/4 of 1/5?
So 1/4 of 1/5 was 1/20. But I don't have just 1/4. I have 3 1/4. So I'm going to scale from the 1/4 to the 3/4 times 3. 3 times as many. So then instead of only 1/20, I have 3 20ths.
Nice. Nicely done. And I wonder, when I said the problem, I should have said I was going to write down 3/4 times 1/5. Because I said, if 1/4 of 1/5 is 1/20, what's 3/4 of 1/5? And I wrote down 3/4, 3 divided by 4 times 1 divided by 5. And I wonder if, based on what you just said, I might write right under that. I might write 3 times with parentheses. So 3 parentheses, 1/4 times 1/5. And I wonder if that gives everybody kind of that scaling feel just a little bit that I can.
Yeah.
It's a 1/4 of time. It's 1/4 times 1/5, but 3 times that. And you're saying that we can think of that as 3 20ths. Cool. So another way that I could represent that 3/4 times 1/5 is I could have represented last time when we talked about 1/4 of a fifth, I kind of drew a candy bar, and we talked about an ant walking down 1/4 of the height. And then over 1/5 of the width, and we kind of had 1/4 of 1/5 was one sort of shaded rectangle inside the candy bar. And if 1/4 of 1/5 is that shaded rectangle in the top left-hand corner, and now I have 3/4 of 1/5, then I could kind of think about that 1/5 of the candy bar, but I don't only need 1/4 of it. Now I need 3 1/4. And so I could sort of picture 3 rectangles in that first column.
Those little slivers.
Yeah. Can you tell me what you've did you draw what I was?
I didn't, but I'm picturing it. So that long candy bar we talked about that we cut into fifths, that first fifth on the left side. Last week we talked about just the one little sliver that was 1/4 of 1/5. And now you have 3 of those slivers, 3 of the fourths inside the 1/5. 3 of 1/4 of the 1/5 of the candy bar.
And so are your 3 slivers going down?
They are.
Yeah. Okay, cool. So we might have listeners going, yeah, that's kind of like if you cut the candy bar into fifths and vertically, and you cut the candy bar into fourths horizontally, and you shaded 3. You could do that really procedurally, but you can also actually really think about, if I know what 1/4 of 1/5 is, it's that little rectangle in the top left-hand corner, but I need 3 of them. Then you really can just like scale and see those 3 rectangles now down that first column. Okay, cool. So the next problem that I'm going to ask you is, let's see, you just said 3/4 of 1/5 is 3 20ths. Now I'm going to ask you for 2/5. Actually, let me restate that problem. Sorry. 3/4 times 1/5, you said was 3/20. I'm just going to restate that same problem that we just did, but I'm going to restate it as 1/5 of 3/4. Is it okay if I use the commutative property a little bit there?
Sure.
So you're saying that 1/5 of 3/4, and I just wrote that down, 1/5 times 3/4 is 3/20. We just established that. The next problem is, what is 2/1/5 times 3/4?
So this is just, I'm scaling again, except instead of scaling the 3/4, this time I'm scaling the 1/5 to 2/5. So 3/4 of 1/5 is 3/20. But now I need twice as many because I'm scaling times 2. So it's going to be 6/20.
So you scale the 3/20 times 2, and that's 6/20.
Yeah.
Cool. And if you were to say that in class, I might go up to that same rectangle that I have on the board where I had the 1/4 by 1/5 kind of shaded in. And then we tripled that. We scaled it times 3. And so I had 3 of those rectangles going down that first fifth in the left-hand side. But now you just said we need twice as many of that. So I've sort of taken those 3 rectangles in that left-hand column, and I've doubled it. I've scaled it. If you see my hand, I've kind of flipped my hand over. Like, it's like I'm taking those 3 and I'm like, it's like, and now I have those 3 in the second column as well. So now I have 6 total pieces I have 6 pieces out of the 20 total pieces, which is the same 6/20 that you just said.
Yep.
But visually, here's what I didn't do. I didn't do what I've seen, and what I was shown to do is like cut it into fifths, cut it into fourths, shade this number 4, shade that number fifths, and then count 6 out of the total, count 20. Instead, I really thought about that 1/20th, and I scaled that times 3. And then I took those 3/20ths and I doubled them, and because it was 2/1/5 now. And so I just doubled those. 3 doubled is 6. Bam. So 2/5 times 3/4 is 6/20. What do you think?
I like it. I am sitting here thinking about, if I'm not in the midst of a problem string, how do I think about scaling? And I don't know if it's a good time to mention that, but I'll wait. I'll wait till we're done.
Are you sure?
Yeah, that's fine.
Okay, cool. So then let me ask you the next question in the string. What is 1/3 of 1/4?
1/3 of 1/4. That would be a 12th.
And can you just give me some why?
If I have a 1/4 of a candy bar and I cut that one, so I have a whole candy bar, I have a 1/4 of the candy bar, picturing that left side again. If I cut that 1/4 into 3 pieces, then I just have 1 of the 12 total pieces of the candy bar.
Cool. And so I could draw that, and I could kind of picture of this candy bar. I've got a 1/3 on the left-hand side and a 1/4 across the top. And that's 1 piece out of the total 12 pieces. Cool. And so what if the next question was 2/3 of 1/4?
So I've double, from 1/3 to 2/3, I have twice as many. So then I'm going from 1/12 to 2/12, which is actually a 1/6.
And I wonder, when you're at that 2/12, if you could actually, so if you were to say that in class, I was saying I have twice as many. So I have that candy bar drawn up there. I have that one rectangle in the top left-hand corner that's a 1/3 by a 1/4. And then you doubled that. So now I've shaded in the one right underneath it. So that's 2 1/3 by 1/4. And I can clearly see that's 2 out of those 12 pieces. How can you see that that's 1 out of 6 pieces? Where are your 6 pieces that chunk of 2 is 1 out of those? Does that make sense?
I think I don't know that I understood your words, but I know what you're getting at. So if 2 of those, so I have them side by side. So if 2 of my slivers now becomes 1 of the units, 1 of the amounts,
you're going to see it as a unit. You're seeing it as a chunk.
There's only 6 of those now instead of 12.
So there's 6 2 pieces. So if you look at that candy bar, you can go circle 2 pieces, and there's 6 of them. The way my candy bar looks like, I have to circle some pieces along the bottom to make them 2 pieces. Mm-hmm. But I can find a bunch of 2 chunkers, and I can find 6 of them. And you're saying we've got one of those. Nicely done. Cool. So you're saying that 2/3 of 1/4 is 2/12, which is equivalent to 1/6. Mm-hmm. I'm going to say that slightly differently, or I just using the commutative property. So 1/4 of 2/3, you're saying is 2/12, which is equal to 1/6. Cool. Mm-hmm. The next problem is, what is 3/4 of 2/3? 3/1/4 of 2/3, because you just told me what 1/4 of 2/3 is. What's 3/1/4 of 2/3?
So I'm just going to scale again from what I had before. Mm-hmm. I'm going to scale times 3. And so I have 1/6 times 3, which is 3/6. And so that's a half.
And 3/6 is a half. Can you see 3/6?
I totally abandoned my picture. Sorry.
That's okay, because you're just scaling.
Yeah.
So we totally could. We could go on that picture where we had the 1/4 of 2/3 being that 1/6, and we could take that 1/6, that 2 chunkers, and we had 1 out of the 6, and we could literally do 3 of them. And when we do 3 of them on my picture, I've got 6 out of the total 12, which is 1/2. I've also got 3 2 chunkers out of the total 6 2 chunkers, which is also 1/2. And you can actually see that it's 1/2 of the candy bar, because I've got 1 6 chunker out of the 2 6 chunkers that make up that 12 candy bar, or the 12 pieces of the candy bar. Cool. So in a way, Kim, what I just heard you say is, if you can think about 1/3 of 1/4 being 1/12, then when you think about 2/3 of a fourth, you can just scale that up times 2. That's just 2/12.
Yeah.
And if you know that 2/3, or that 1/4 of 2/3 is that 2/12, then you could also think about 3/1/4 of that 2/3 is just scaling that up times 3. And so you could take that 2/12 and scale that up times 3, and 2 times 3 is 6. So that's 6/12.
Yeah.
And then you could, if you have to, simplify at the end.
Yeah.
So go ahead.
Well, I was going to say, what I was going to mention earlier is that, sometimes people will suggest that in a problem string, well, yeah, Kim can follow what you're saying, or a student can follow what you're saying, because you're giving them the problems that are the helper problems.
You're leading them by the nose. You're like, do this, do this, do this. Bam.
And I think what I'd like to suggest is that, because I have built understanding, or if we would help kids build understanding of a unit fraction times a unit fraction, like that's so within their knowledge base and their understanding, then a student could look at a fraction multiplication problem like 2/3 times 3/4, and they could say to themselves, what is 1/3 times 1/4? That's 1/12. And I could scale up by 2, scale it by 3, or scale it by 6. And so they can lean on the fraction understanding and scale for themselves, double scale or scale all at once, but it still has a meaning to it.
Yeah, you're actually suggesting that instead of looking at a fraction multiplication question and reaching for a rule, which rule is this? Is that the one we did on Tuesday, or is that the one we did on Thursday? Yeah. Instead of reaching for a rule, they can say to themselves, what do I know? Well, I know what a unit fraction times a unit fraction is. So I can find the total number of pieces. And then I'm just going to scale times the first numerator and scale times the second numerator. If they have experience doing that, they can literally think about fraction multiplication just like that.
Yeah.
Like unit fraction times unit fraction, bam, I know the total number of pieces.
Yeah.
Scale times the first numerator, scale times the second numerator, bam. What they literally just thought through was multiplying the denominators. Isn't that interesting? They multiply the denominators first to find the total number of pieces. And then they scaled times the numerator, scaled times the other numerator. They multiplied the numerators together. And they end up with multiplying the numerators divided by multiplying the denominators. But they've reasoned through it in such a way that now everything else is going to follow with more meaning from there. Mm-hmm. Yeah, it's so interesting. I wish I had learned to reason about fractions that way. Kim, I remember the day when I was working on writing lessons and activities for building powerful numeracy, and I was doing some stuff with the area model for fractions, the kind of more memorize, rote, county way, where I would divide the rectangle, maybe I should say divide the rectangle and shade, divide the rectangle the other way and shade. And then I would look at the double shaded piece and count, really. Mm-hmm. And I remember I was checking some work that I was doing, and I asked my kid, I was like, hey, how do you think about this fraction? And he did kind of what we just talked about. And I was like, wait, what? And then I called you and I was like, hey, how would you think about this? And you did something different. And I was like, like, yeah. Maybe I need to rethink a lot of, and I just was aware in that moment how little I had ever thought about, like actually reasoning with fractions. The more I dove into reasoning about fractions, the more it influenced so much other work that I was doing. So many other things now I look at differently. Even the slope of a line I look at differently now that I can reason about fractions differently. Yeah. It just impacts scaling everywhere in really, really interesting ways.
Yeah. All right. But we're not done. So we've talked unit fraction by unit fraction. We spent some time with scaling this week, and there's more. And this is when it gets really fun. So I hope you join us next week.
Yeah, I wonder if anybody's thinking right now, but Pam, what about simplifying those fractions? What about, well, you just join us next week. Let's have some fun with that. All right, y'all, thank you for tuning in and teaching more and more real math. To find out more about the Math is Figureoutable movement, visit mathisfigureoutable.com. Let's keep spreading the word that math is figureoutable.